Uh-huh. Okay, alkyne reactions. Alkynes. Alkynes of fun here. Twice the fun. Any questions before we get going today? TLC lab this week. Pre-lab downstairs. I'll be returning at least one or hopefully two things during lab. Okay. Test. When's test? Monday. Okay. I won't be here on Monday. I can get someone to give the test for me.
Or we can Wednesday seems like a great option.
So we can ask questions.
Yes.
Okay. Yeah, I'm not so keen on someone giving it for me. It will not, we only got 55 minutes and we need to move quickly, and I think I can move quickly. I think the test needs to be on Wednesday. Okay. New material though. Hopefully this is the last time I'll be out, but we'll have to do another lecture video, and I'm probably going to do it on resonance. Resonance is a broad topic. I think it's suitable for lecture video. Also during test 3 we'll have mass spec. Mass spec is covered by video only, like IR. Mass spec will not be as involved as IR. It's a new analytical technique, not quite as much as IR, but it is involved. Important technique, that'll be for test 3. No spectroscopy on test 2, which is next Wednesday. Okay? And if you have people organic 1 or organic 2, that'll be the only test you have for me that does not have spectroscopy. Test 2 next week. Okay, hydration. Any questions? Tautomers, yeah? Relocation of how many H's?
1 H.
Okay, where are we at? Hydrogenation. Okay, so just like alkenes, we can hydrogenate an alkyne. Twice the fun though. Hydrogenate once, you get the alkene, but it's going to be cis, right? Because where do the two H's come from? From the metal surface, boom, like two darts. The two H's are on the same side, so the two existing groups, if they are there, will be on the same side. They get pushed to that side when the H's come in. Okay? Throw two H's at my shoulders. Boom, two H's, these move back to make room for the two H's. These are cis, the two H's are cis. Right? But we can hydrogenate again, and the alkene becomes alkane, and with the alkane there's no stereochemistry. You have free rotation, conformers. Okay, double the fun. If you want to stop with the alkene, how you do it, you use a poison catalyst. The most common is Lindlar's catalyst. It's a mixture of palladium. There's some other things. Certain compounds are known to poison the catalyst because other compounds will stick to that metal surface and sort of tie up the metal. Amines will do that. Also sulfur compounds will do that. So the catalyst can be poisoned. It can become made weaker, less active. If you use a poison catalyst, it will typically still work and get to here, but it won't continue on. That implies that the first reduction is easier. Reduction, is it hydrogenation or a reduction? Well, it's both, because typically when you add hydrogens, that's called a reduction in organic chemistry. Okay? Removing hydrogens is typically called oxidation. In Gen Chem, you do redox based on oxidation numbers. Loss and gain of electrons, oil rig, yeah? Okay. Organic chemistry, adding H's is the reduction, removing H's is an oxidation. So hydrogenation can also be called a reduction. Okay? So you can partially reduce the alkyne to the cis-alkene. If you wanted to stop there, you have to use a poison catalyst, and it actually will not continue on. What about if transalkene. We know how to make cis alkenes from alkynes, and you make a transalkene. Oh, yes, you can. This would be a partial reduction. Is it a reduction? What are we doing here? If you look at formula, we are adding two H's. Right? There's a new H there, and there's a new H here. We've added H's, we can call it a reduction. It's not a hydrogenation, though. We're not using hydrogen. We're using sodium metal. I can put an oxidation state of 0, sodium metal. It's not sodium plus. It's just sodium, neutral sodium, metal. And ammonia. And we do it at cold temperature, minus 33 degrees. Why not minus 32 or 34? Well, minus 33 is the temperature at which gaseous ammonia becomes a liquid. Okay? Now you could probably do it at minus 34 because ammonia would be a liquid at minus 34 and minus 35. But minus 33 is the temperature, it's basically the boiling point of ammonia. Because if you're coming the other way, it's a liquid at minus 50. And when you warm it up to minus 33, it comes from a liquid to a gas. At room temperature, which is warmer than minus 33, it's a gas. Going the other way, if we go below 33 or below, negative 33 or below, it's a liquid. This reaction is done sodium metal and liquid ammonia. Okay, liquid. It's a unique solvent, but it's can be used. This is ultimately called a dissolving metal reduction whenever we use metals. And at the end, it will be dissolved. We'll see why. Obviously, the H's come from where? Not from the sodium, but
Ammonia.
from the ammonia. Okay. How do they come from ammonia? This reaction is actually a radical reaction. And it's our first look at a radical reaction. First thing is, if you take sodium, and put it in ammonia, what does sodium like to do chemically? What do you know about sodium, the reactions or whatnot? What does it like to do? Give away what?
An electron gives away.
It likes to give away one electron, so it becomes like neon. Okay, it likes to become sodium plus. Yes. It gives away an electron. Where does it give it to?
The alkene.
Well, there's no alkene here yet, or alkyne. You just put sodium and ammonia.
To the hydrogen.
You'll just get free electrons. It's sort of a miracle, interesting miracle of nature. Mother Nature, crazy, wild, and chemist. Electrons. And we can show this as an E minus or maybe a dot. Okay, like a single electron. If there was two, we could show maybe a lone pair. That's electron. And the ammonia will solvate it by sort of hydrogen bonding. I don't know if you officially call this hydrogen bonding. I mean, this looks like a H bond. Donor and the acceptor would be lone pair on an O, N, or F. Well, that's not even a lone pair, it's just one. It's not a pair, it's a single electron. Basically, this is called solvated electrons. very interesting. Here's one thing, and I don't know who the first chemist to ever do this was, but if you take liquid ammonia is colorless, watercolor, colorless. Okay? You put sodium in it, and it becomes blue, bright blue, blue like this jacket here, shirt, yeah. Okay? What's going on? Something. Well, this is going on. The electrons are being sort of released from the sodium, and they're being solvated by the ammonia. What causes it to be blue? I don't know that I can tell you. I know I can tell you this. Very often radicals, single electrons, tend to be highly colored. So that's an indication there. But I can't tell you why. So I'm telling you Bill Gates is rich because he has lots of money. Okay? It's blue because it's a radical. But I can't tell you why it's blue because it's a radical. Okay? Question?
Can anyone explain that, or is that
Yeah,
just
I just
okay?
don't know.
Okay, I just didn't know if I could like do research.
You can look it up and see. But very often things that are highly colored, well, what comes first, chicken or egg? Things that are radicals often are highly colored. Can be. Okay. There's some examples. Somebody can look into that. Solvate electrons, very brilliantly blue. There's a video on the YouTube channel, I think, that shows this. Okay. There's two videos. The other one goes with the stuff below. There's a picture below. Okay. Solvate electrons. Okay. Now you can put in your alkyne. Basically, we have electrons. And the electron, I'll show it as a dot maybe here. Basically, instead of working with a lone pair, two dots, I've got just one dot. It's a single electron. And a single electron actually pumps into this pi bond. Okay? Bam. Here we go. Whenever you move a lone pair, okay, we use a regular arrow that we've always been using. If you move a single electron, you use what's called a fishhook arrow. Okay? Mechanism arrows. So I'm using, on the end, it's a fishhook, or just a half arrow on the end. So I use to move a single electron. It pumps in here. These two, the bonding pair moves here. I'm moving two electrons there. Pi bond. I'm taking the two electrons and I'm moving them onto the carbon. Okay? What does that electron arrow movement give? This is not a mechanism arrow. This is a progression arrow. Okay? We're going to the next. Okay? What do we have here now? This here. We have that. It's not complete. Are we adding an electron to this carbon? What that arrow means? Carbon now has a single electron. What are we doing here? Moving the pi bond, the two electron covalent pi bond, onto the carbon to become what? Lone pair, two electrons. Okay? Are we complete? What's missing here?
Charge.
Charge. Because that's a neutral thing. Let's charge an electron. Negative. I drew the negative. Okay? That's usually drawn like that. Usually I would want to circle my charges. It's very common to kind of draw the electron like this. It looks a little funny circled, but it's just circled. Okay. If you react a neutral with one electron, which is minus, you should form something that's minus. Where's the minus at? This carbon is minus. You count electrons minus. What's the charge of this carbon? Neutral. It's neutral. It owns 4. It ain't standard, but it is neutral. There you go. We get that. Why did I draw my two methyls trans? Which is better, cis or trans? Trans. It has a choice. And that right there, that's why you get trans. Okay? We could go through that. I could draw the same thing with the methyl cis. Okay? It has a choice. When that comes in, the group can go either way. But guess what? Transition state leading to these. Which is more stable, left or right? Right. Thus, the transition state leading to it is going to typically be more slower. So, when water's running down the road, does it run uphill or downhill? Downhill. So the energy flow is going to go low to this. Why would it go uphill if it doesn't have to? Okay, the water running down the road has a choice. I'm going to go down this road. Okay? We had a choice. Basically, you can go back and understand that choice. Transition state leading to this is going to be lower. Okay, here you go. They're trans. What do we need to get on these carbons? H's. Where can an H come from?
Ammonia.
Only place is ammonia. Okay, here we go. Is ammonia an acid or a base?
It's an acid here, I guess.
Well, you're told and told and told it's a base, okay? Base, but well, it's fixed to be an acid. Okay? Now these electrons will take an H from ammonia. Okay? Standard acid-base reaction. What does this give? What's down on the carbon? H. Plus what? NH2. NH2, how many lone pairs on this nitrogen? 2. How do you know 2? Well, there's one there to begin with, because I know a Lewis structure. And the second one comes from my acid-base mechanism, because these electrons move on to nitrogen. That's how I know it's 2. What's the charge of this nitrogen? Minus. So there's about a half a dozen things we talked about just right there. Okay? Everybody good? Does that acid-base reaction give those two properties? Yes. By the way, we didn't say what else was formed back over here. When sodium metal gives up an electron, you have electron solvated plus what? Na plus. Yes. Don't forget about that. So there's an Na plus here. That's all neutral. If you got a minus, you got to have a plus. What's the plus? Na plus that was formed. Okay? There we go. Okay, at this point, we need another electron. And another electron comes in here and teams up with this one. And that gives what? It's now 2 electrons called a lone pair, and now this thing is minus. Because if a neutral reacts with an electron, which is minus, you should form a minus, right? So where did this electron come from? How many electrons does sodium supply? 1. There it is. So where did this one come from? The second sodium. Okay? We'll balance this equation in a little bit. Second sodium comes in, gives up another electron. We get to this point. Now, what do we need to do here? We're just repeating the process. These electrons take an H, these electrons stay here. What do we get? Well, that gives this. And we also formed another NH2 minus. So this reaction is known to take place. This is the best theory for how it takes place, mechanism. Unless somebody else has a better mechanism. Anybody else has something better to propose? What do you call something that has a single electron, unpaired electron?
Radical.
Radical. Ammonia is serving as an acid. Serving as a solvent and an acid. Okay, so next time you take Gen Chem, they say ammonia is a base. Say, well, I know an example where it's an acid and a solvent. Let's balance this reaction. How many sodiums do we need to do this? Two. It's actually two. Right there. How many ammonias do we need to do this?
Two.
Two, yes. Okay? And this is this side. So over here we have, well, that's 4 carbons and that's 4 carbons. Let's forget the methyls. There's no H's in between. There's now 2 H's there. Well, let's finish it. What's over here? Okay, we'll write it here in the bottom. This plus what's formed? 2 Na pluses plus what? 2 NH2 minuses. I agree. And if you can somehow, however you want to show that mechanism, that's balanced reaction. Okay? Can we do this? Instead of showing these as ions, can I just show it as 2 NH2s? Don't write this, but if I had 2 Na pluses and 2 Cl minuses, is it okay to just show that as two of those? Yeah, that's what that is. I mean, when you see sodium chloride, don't you see Na plus? Well, there's 2 Na plus. And when you see that, don't you see Cl minus? Well, there's 2 of those. Okay. Same thing there. Can I just show that as 2 NaNH2s? Because if you see NaNH2, don't you know sodium is plus? It always is. If it's with something else. It ain't here because this is just pure sodium. And if sodium is plus, then H2 is thus minus. Okay, you good? Yes. And so we make this. How many H's here? 4. And how many H's here?
6.
Where'd the other 2 go? They're over there now. Everything's balanced now, right? Okay. Now, metals are not soluble, but the sodium salt up there, the NaNH2, is going to be soluble. And so this is called dissolving metal reduction, because as the reaction progresses, and at the end, the sodium is gone. Where did it go? It dissolved. It's not really gone, it's just now dissolved, it's soluble. Just like when you put sugar in water to make your iced tea or something, it ain't gone, it's just dissolved. Okay? But so a dissolving metal reduction, that's a very broad term for when you use a metal and at the end it's dissolved. Because it reacted, it became an ion usually. Okay, this is a radical reaction. Okay. Radicals. Very big back in the 1960s, particularly out in San Francisco area, California. Radicals. Okay. Remember the 60s? 1960s. Very, very colorful shirts. Okay. Radicals. Any questions about this reaction? There's a video on the YouTube page which shows some sodium being put into ammonia, the color. Then I think the ammonia is evaporated off and the color goes away. Because the electrons only become solvated with the ammonia. If the ammonia is gone, I think the electrons go back to the sodium. It's very intriguing. I mean, you can take a look and see if you can read about it any. See what the textbooks say. Okay. So what do we know now? What do we have to add to our toolbox? We have a way to convert alkynes to transalkenes. The previous page showed a way to get to cis-alkenes. Cis-alkenes come from what?
Poison.
Partial hydrogenation using a poison catalyst. So there the H's come in from the same side. Questions? What I said earlier is, I wonder who was the first chemist or scientist or person to put some sodium in ammonia and see this blue color, brilliant blue color. Can you imagine the fascination of seeing that? What happened here? And then someone said, well, let's put in an alkyne and let's, who decided to do this? And then somebody was like, well, let's see what we got. And then they somehow, well, let's distill it. And we got a product. It's an alkene now. Wonder what happened. How do we know it's an alkene? Well, it ain't what I started with. But you can have an answer for all these questions, right? How do we know it? How do we know the alkyne became an alkene? How do we know it's cis and not trans?
I had a few.
How would? Well, I mean, everything has been answered along the way. I'm just getting you to think, hey, these are the things that we've talked about. I mean, this is how organic chemistry is. How do you know it's cis or trans? If that's the question, I don't know that we've done anything to tell that yet, because I don't think you can tell between IR, unless, I mean, once you know which IR is which, you can just match them up. But how do you know which is which at the beginning? NMR would be better for determining cis or trans, and that would be covered organic too. But again, all these questions are, if you're going to do chemistry, these are questions you're going to be asking along the way, and you've got to be able to have answers to. And that's what the course is about. We'll address these questions. And right now, what we just did is mechanism, and that's the how. How did this reaction take place? Do we just want to call it magic, or do we want to have some understanding of electrons moving and reacting? And questions?
I have a question regarding the poison catalyst. Is the way to differentiate between a poison catalyst and just the metal is just the metal is by itself, so it would rearrange, and then the poison catalyst is just like palladium with something?
Usually you're going to add something to it.
Okay.
A word would be called a dopant.
Okay, don't.
The poison. And like amines will serve as poison, sulfur compounds. But a lot of times heavy metals, barium and lead, will basically adhere to that metal surface and cause it to be less active.
Okay.
You ever heard of catalytic converters in cars?
Here.
Okay, they can go bad because the metal just gets somehow compromised. But that happens over time, maybe from pollution or something. You can do that on purpose if you want the metal to become bad. And what we know is if you make it become bad and less active, it will still do the first reduction, but it will not do the second. And then there are lots of questions of why and all that. At some point we have to just end the discussion. But keep in mind, the most common poison catalyst is Lindlar's catalyst. If you ever seen Lindlar's, just know that's a poison catalyst. You can look it up. Try Wikipedia. Great resource. Okay, do you ever heard of Wikipedia? Okay, all right. You can have a discussion there. Okay. Anybody tell you not to go to Wikipedia?
Yes.
What about books? Do they tell you not to go to books either?
No.
Because people write Wikipedia, people write books. Why do you trust books but not Wikipedia? Okay. Is it because it's been peer reviewed? Well, people peer review Wikipedia all the time. Okay. In the end, I would trust nothing you read. I don't trust anything I read. I read it and I make conclusions myself. Okay? All right, everybody good? Everything you read, you have to say, does this make sense? Yeah? Okay. Can I confirm this by reading it somewhere else and have a collection of resources that give me more confidence in what I'm reading? But Wikipedia is quick. I get there in 2 seconds and I can read all about Lemlar's callus. And I can decide if what I'm reading is... Okay? Where did I get the molecule of the day from? Okay, look it up. Right there. I think that molecule is also in honeybees. I believe that's the one. And some bees recruit other bees to come do work. How do they do it? Do they make a phone call? No, they send out chemical messengers, pheromones, and these chemicals make the other bees do stuff. Pheromone. That's a pheromone. It's basically a pheromone is a hormone that is outside the body. Instead of the hormone telling your body to do something, you're having a chemical that's telling the other. Okay, pheromone. Okay, so that's the biology for the day. There we go, dissolving metal reduction. Fascinating reaction. Look at the YouTube video with the ammonia. Last topic before the test. Acidity of terminal alkynes. Okay, a terminal alkyne has a pK of about 25. That's not that acidic. Water is about 16. But it's acidic enough that we can do chemistry with. And if we have a strong enough base, we can remove this H. N-butyl lithium. N just means normal, straight chain. Basically, it's a carbanion there. Butyl carbanion. And of course, the lithium cation. Lithium is just most common with carbanions. Plain carbanions. You could theoretically have sodium or potassium. It's just most common. Okay, already said. One of the strongest bases you can have. Because carbon just does not like being minus. This can be formed and used, very strong base. And these electrons will take the H, all right, make bond to H, and these electrons will move here. Same old acid-base reaction. What does that give? Well, when that takes an H, it just becomes butane. You can look at structure. Everything has H. It's just 4-carbon alkane. But what does this become? Electrons move here. Over there. There's your anion. Okay. This is sometimes called alkynide, alkynide, like chloride. That's not used that much. Very often it's called an acetylide anion because what's acetylene? Acetylene is the simplest alkyne you can have. What do you use acetylene for? Anybody? It's a gas. You use a torch. Acetylene torches. Anybody? Yeah. Okay. Torch gas. But it's the simplest, and sometimes, even though this is not acetylene here, the term acetylide is a common term for just any alkyne anion. This is a less common term. Okay? So we can make the acetylide anion by reacting with N-butyl lithium. How do you judge pK equilibrium? Which sides would be favored? This has 25. Butane is just hydrocarbon. No acidity at all. 40. Which side's favored?
Right side.
Right. This side's favored by how much?
10
10 to the 15. That's a huge number. So, will this chemistry happen?
Yes.
Yes. N-butyl lithium is strong enough to deprotonate the terminal alkyne and to form your acetylide anion. Look, you're using one carbanion to form another carbanion, a carbon anion. Why does this reaction go that way? This is more stable than that. Why is that more stable than that one? Because this is in what type of orbital? SP, but this is in what type of orbital? SP3. Which one's more stable?
More S character.
SP. You see how we're going to a more stable? Well, that's why the equilibrium is favored that way. That's why the pKa's are different. It's all there. So there's a classical hybridization effect. And if you look back on the handout from test 1, acid-base handout, one of the important topics was hybridization. And if you look at that section, I showed that reaction right there, or talked about. Okay? Another base you can use is this. Have we seen that before?
Yes.
Na+?
Just
We formed that in the previous reaction. That, by the way, is called sodium amide. What's an amide? Amide. Amide. It sounds like a functional group. Chlorine, chloride. Bromine, bromide. Acetylene, acetylide. Amine, amide. See, nitrogen anions are called amides, amides. And that's kind of unfortunate because there's also a functional group that's called an amide. All right? So, but this is called sodium amide. His short name is called sodamide. Shorten that together. Sodamide. Okay? Sodamide there. This is NH2 minus, right? These electrons take the H, these stay behind, we get this. By the way, the cation says, get that right, plus what? What are we forming there? Ammonia, ppF 35, 25, which side's favored? Product. Is sodamide strong enough to deprotonate a terminal alkyne? Yes, both of those bases are. What if we use hydroxide? Well, the answer's already here. Hydroxide, more standard base. These electrons take the H, these stay behind. What do we get? That plus water, right? Making water there. That's 16. Which side's favored? 25 or 16?
25.
Nah, this side's favored. Question, is hydroxide strong enough to deprotonate this?
No.
No, it ain't going that way fully. Okay? In the end, you cannot use a common hydroxide base. You have to use stronger bases. Are these stronger? Why is that a stronger base? Or let's turn it around. Why is this a weaker base than that? Because oxygen's a better parent. It likes being minus. Right? All right, so everything's there. So actually, which side's favored here? To the right or to the left? To the left is favored. Can I just turn this reaction around and show it like this? So that's not favored. Instead, this is favored. What is favored? Okay? This is the point where you guys look at things and never really see what it is. What is favored here? What is favored is if you put an alkyne, acetylide anion in water, if you mix this with water, what's going to happen? What will it do to the carbanion?
Protonate it?
It will protonate it. It will put the H back on. Isn't that what this is telling you? This is favored. If you put that in water, it's going to go this way and put the H back on? Yes. Can I just show that going to the right? Yes. There's water. What is this? Calcium carbide. Can you draw a Lewis structure for that? CaC2. That's awfully simple. Well, if you draw a structure for that, it is the C2 is this. And the calcium that has what charge? 2 plus. There you go. You got 2 minuses, balanced with a 2 plus. CaC2. Well, calcium I, carbon is minus. That's a 2 carbon. calcium carbide is actually, can actually be made from like base materials. You take like calcium hydroxide and carbon, I don't know how it's done, but calcium carbide has been made for many, many long years, hundreds, thousands of years. Taking just base stuff and heating it very hot. It can be made. But then water's around. You can find water lots of places for many thousands of years. Okay? So these two things can be mixed, and when you mix them, what are you going to get? What happens if you put carbanions in water?
They'll be,
Don't we protonate them? Yes, we just said that. And if you protonate them, what do you get? Acetylene. There's acetylene. And the calcium will sit with, what did this become when this took H? Hydroxide, you're going to make two of those. So there's your calcium hydroxide. Okay? Isn't it great to see how everything's balanced and everything makes sense and it's all there? Everybody seen it? Okay? It ain't magic. So what's the relevancy of this? We're just showing the reverse of that. I'm showing you calcium carbide, which has been made forever, and you can look it up. Wikipedia will tell you more about all this. Okay? It's a way to generate acetylene. What do you use acetylene for? Torches. Okay? But you can also use it for other things to burn. Back in before flashlight, battery-operated flashlights came around, these chemical flashlights. And you would take calcium carbide and put in there in a little chamber and have water there and have them mix. When they mix, what did it produce? And then you have a port where that gas coming out and you can light it. Like lighting your grill. Okay? Instead of a propane tank, you have a mechanism where these two are mixing, and then the acetylene comes out, and you light it, and it will have a continuous stream. Now, I don't know why it just doesn't explode, but again, this can be created up, and so your grill doesn't explode. How does it burn nicely and not just? No, this can be done. Technology, I mean, a nice even flow of the gas. Okay, there's a video that shows someone doing this, putting in calcium carbide. This is a solid. And then filling it with water and you're putting it there and then they light it. Okay, so that's the second video we'll look at there related. That's a question.
Would it be two H2O? One minus.
You want to balance that reaction?
Yes.
You're welcome to balance it. Yeah. I rarely balance reactions. I did it up top, but that was free. Okay? You want me to balance the other ones? Okay? Yeah, it looks like it's not balanced. But still, you take calcium carbide and react it with water. So it's a very relevant reaction, understanding the chemistry and then some application to the monitor film. And not only can you have a flashlight, but they used to have helmets. Okay? Can you imagine wearing a helmet? It's got this flame up there.
it's so scary.
Put your water in, your calcium carbide, light it. Because I mean, you had to do what you had to do if you were in a cave or something, digging for coal back in 1820 or something, to be able to see. Also, you like to have two hands, so you put the light up here. You have a little flame burning up there. Okay. In the end, guys, relevancy, but everybody understand the chemistry here? This is the reverse of that, and we know that carbanions will react with water to protonate, and when you protonate, you've got acetylene, which is a gas that can be burned. All right. Now, we will revisit this when we get to test 3. Okay? Because in test 3, we will use these carbanions, these acetylene anions, for other things, not just protonate them, but for other chemistry. And when we get over there, I'll say, hey guys, remember how we deprotonated terminal alkynes? Okay? And you guys will go. And I'll say, remember the very last thing we talked about before the end of test 2 material? And you'll go, okay? Remember this time. That's it right there. Okay? That's the end of test 2 material. What do we need to talk about for review? On Friday, we'll have our third quiz for the material, including alkyne chemistry. Okay? Alkyne chemistry, stereochemistry, really should be over everything, but we need to see how we're doing in preparation for next Wednesday. Yeah? Got a couple minutes left. Any questions? Look at the schedule. We're set to begin new material on Friday. It will not be on the test, but okay. I'd like to give you a day or two more to work on it. All right. Start new material. We will have a quiz. Any questions, though, with the couple minutes we have left? Yes?
Oh, will it also Monday?
I'll have to think about it further, but at this point, probably not. Because I'll probably just have a video, and that will be sort of consider that your class. Other questions?
For the trans-alkene reaction, how would you perform that in a lab setting? Because the boiling point of ammonia is so low.
Ammonia would be in a tank, gas tank. You can put it into a flask. You got to have the flask cold. And there's ways to get it cold, dry ice. If you pump that gas in there, you'll see it go from a gas down to a liquid as it cools. It's condensing. Okay? Just like you see a gas in your distillation condenses. I mean, it's gas here, and then it comes out as a liquid. Somewhere between, it went from gas to liquid. Well, the condenser condensed it. So the condenser is cool. Well, if you run ammonia gas through something cold, it will condense it down to a liquid. You got to keep it cold. If you let it warm up, it's going to all evaporate. Keep it cold. Keep it cold. Okay, like you keep your beverage cold. Okay. And then you get the alkyne in there and your chemistry. And at the end, ammonia is easy to get rid of. Let it warm up, it'll evaporate. You just got to be careful. You just want it to evaporate into the air, or do you want to trap it somewhere? But watch the video, because I think they'll condense it. They actually make the ammonia. I said a gas tank. Well, you can make ammonia from like ammonium chloride, which is a solid. You treat that with a base, it'll generate ammonia. Then you can take that gas and pump it into a cold flask and condense it. Watch the video and I'll show you a little bit. A little louder.
For the lab tomorrow, when we're talking about the solvents that we're putting plate into, like it says 10%
Ethyl acetate.
ethyl acetate and saying things like that. Are we going to be given those mixtures? Or
They're already made. Yeah. Those mixtures are made. A little yeah. You can use just different solvents. It's very common to use mixtures, because there's only so many solvents. Mixtures will allow you more variability in your polarity. So it's very common to see mixtures with TLC. The more polar one you have in there, the more polar your mixture will be. TLC is very, very important, analytical technique, and we'll use